Hi, welcome. In this unit, we're going to learn about waves. A wave is a disturbance that carries energy through matter, or another word for matter is medium or space. Space is a lack of a medium without transferring the matter. So space, or another word for space, is vacuum. So a wave is a disturbance that carries energy either through matter or through a lack of matter without transferring the matter. A tsunami is a type of wave. In the year 2010, a large earthquake off the coast of Japan generated some very large tsunamis and did a lot of damage to the Japanese coast. But we see some pictures here of boats in the Santa Cruz harbor. They were also damaged. How did all the energy required to damage these boats get from Japan to these boats? It got there through waves. The waves traveled across the ocean. There's two types of waves. The first type is called a transverse wave. In a transverse wave, oscillations occur perpendicular to the direction of energy transfer. Ocean waves and light waves are an example. And so are the waves caused by shaking a piece of string. Notice that the person shaking the string is moving the string up and down. That's causing the wave to move up and down and up and down. The wave oscillations are moving in a vertical direction. But notice that the energy is being transferred from his hand to this hook on the wall. So the energy transfer is to the right, or in a horizontal direction. The rope itself doesn't move this direction. The rope itself is oscillating up and down. The next type of wave is a longitudinal wave. Longitudinal waves are sometimes known as compression waves. Longitudinal waves produce oscillations that are parallel to the energy transfer. Sound waves are an example. In this example, a person is holding a spring, and they're pulling the spring back and forth. That's causing the coils in the spring to bunch up in some places. That's known as a compression, and to spread out in other places. The direction of oscillation is back and forth, but like the previous example, the energy transfer is also back and forth. So longitudinal waves travel parallel to the direction of the wave oscillations. So those two terms, it'd be good to have those in your notebook along with the definition. Those make good multiple choice questions for your assessment. Here's some new vocabulary for you, and I'm going to show you a transverse wave, and we're going to identify these. Sorry, the word amplitude got cut off a little by the diagram. But we have wavelength, period, frequency, and amplitude. The wavelength is simply the length of the wave. It's the distance between two consecutive parts of the wave. Let's take a look right here where the wave is crossing the x-axis in a downward direction. I'm going to follow along with my mouse, and it comes right back up here. That is not one wavelength because here we're crossing going up. We're going to have to come all the way up again and go down, and right here, from here to here, is one wavelength. We could also start at the top of the wave, and we can go down, and when we get back to the top, that's one wavelength. From here to here is one wavelength. So in your notebook, draw a picture of this wave and identify a few different wavelengths. Okay, next let's talk about amplitude. A-M-P-L-I-T-U-D-E. You see this line going through the middle of the wave? This is called the equilibrium position. On the diagram you're making for your notebook, please label equilibrium position. The amplitude is the maximum distance from the equilibrium position. So for example, equilibrium is here, and we can go up, and that's one amplitude. The top to the bottom, that's not an amplitude. That's twice the amplitude. it's called peak to peak distance, but amplitude is either from the top to the equilibrium or from the bottom to the equilibrium. Now our diagram here is a still image of a wave, but waves are actually things that move. Let me put up an animation of a transverse wave in motion, and then I'll define for you the period and the frequency. Okay, here's a transverse wave. It's oscillating up and down, and the energy is being transferred from left to right. I'm going to put my mouse right here, and I want you to notice every time a wave crest passes it, we're going to count how many seconds it takes until another wave crest passes it. Ready, set, now. 1, 2. Okay, so it takes about 2 seconds for a wavelength to pass my mouse pointer. Let's try it again. Now, 1, 2. It would work if we did it from the bottom. We'll wait for a wave to catch the mouse. Right now, 1, 2. So the period of this wave is said to be 2 seconds. So earlier in the year, we learned that distance is speed times time. Well, since a wavelength is a distance, we can actually use this formula, but we're not going to use the letter d for a wavelength. We're going to use the Greek letter lambda. Lambda equals velocity times time. Now, if we want, we can isolate v in this formula. We can say v equals lambda over time, and we can isolate time. We can say that time equals lambda over v. And finally, let's talk about frequency. Frequency is how frequently one wavelength passes a certain point. So let's put my mouse right here at the top, and we'll say start when we get a crest, and we'll go start, 1, 2. 2 seconds is a period, but you notice every second a half a wavelength passes by. Here we go. Right here, 1 second later, there's a half a wavelength. 1 second later, half a wavelength. So our period for frequency is simply the reciprocal of period. Frequency equals 1 over time. And we can isolate t if we wish. Time equals 1 over frequency. Well, that means we can take any expression here that has t in it, and we can replace the t with 1 over f. So we could say that lambda equals velocity times 1 over f. Or let's just clean this up a little bit, and we'll say that lambda, which is the wavelength, equals v over f. We can also take this next formula, velocity of the wave equals the wavelength divided by the time. Velocity equals lambda, and where I see a t, I'm going to replace it with a 1 over f. Now, there's nothing wrong with this, but it's not written in a way that would make your math teacher proud. Let's clean this up a little bit. This is going to turn into v equals lambda f. The velocity of a wave is its wavelength multiplied by its frequency. And finally down here, time equals lambda over v, and we can replace time with 1 over f. But we don't want 1 over f isolated, we want f isolated. So we can flip this fraction upside down, provided that we flip the other side of the equation upside down. So this cleans up to frequency equals velocity over wavelength, lambda. Okay, and here are 1, 2, 3, 4, 5, 6 formulas that are going to get you through a lot of your next assignments. And here's 2 more. Here's a few examples so that you can see the relationship between time and frequency. If I can walk around the block in a half an hour, how many times can I walk around the block in 1 hour? And you'd think about that and you'd say, if I could walk around the block in a half hour, then I could walk around the block twice in an hour. What if I could walk around the block in a third of an hour? That's 20 minutes. 1/3 of an hour. Then I should be able to walk around the block 3 times in 1 hour. What if I could walk around the block in 15 minutes? That's 1/4 of an hour. 1/4. How many times can I walk around the block in an hour? That would be 4 times. What if the block was so large that it took me 2 hours to walk around the block? How many times could I walk around the block in an hour? Well, in an hour, I'm not even going to get all the way around it. I'm only going to go halfway. So notice that every number turns into its reciprocal. Time and frequency are the reciprocals of each other. 1/2 becomes 2, 1/3 becomes 3, 1/4 becomes 4, 2 becomes 1/2, etc. The unit of period, recall that period is just how long it takes a wave to travel one wavelength. The unit of period is, because period is an amount of time, the unit of period is any amount of time. Seconds, minutes, hours, years, etc. Typically, in physics, we use seconds as a unit of period. Frequency is how many cycles of the wave pass in 1 second. So the unit of frequency is cycles per second and cycles per second has a nickname. Cycles per second is known as a hertz. And a hertz has an abbreviation. It's capital H, lowercase z. So the unit of frequency is Hz, stands for hertz. Okay, that's enough to get you through a lot of your homework. So I'll be posting more videos as the days progress. So keep logging in. Check for new videos.